Okay, so this is a talk through of the third problem set that I wrote and sent out. Um, so we're going to go ahead and start with number 1 here. And number 1 states copper 2 sulfate can form a number of different hydrates. If a 4.12 gram sample of a particular copper 2 sulfate was heated until all the water, 25.2% of its mass, was driven off, how many water molecules are in a formula unit of copper 2 sulfate hydrate? So, what we first have to realize is that the general formula here is CuSO4 dot XH2O, where X is yet to be determined, and that's the number of water molecules per formula unit here. So what I've given you is a 4.12 gram sample of this, right? So 4.12 gram sample. And we know that 25.2% of its mass is due to the water. So we can actually calculate directly the mass due to water. What we do is we multiply this by 0.252, and this is going to give us the mass of water. And so when we do this, what we get is 1.04, roughly, grams of H2O. Okay? So what does this mean? Well, it means that if we take our 4.12 gram sample and subtract off the 1.04 grams of H2O that was driven off when this was dehydrated, we end up with the mass of just the copper sulfate, right? So what we've actually been able to do is separate this into components. We've got the XH2O, and we've got now the copper sulfate. So let's go ahead and do that. 4.12 minus 1.04, and that gives us about 3.08 grams due to copper sulfate. So what we have here is all the tools that we need to actually determine the formula of this hydrate. Because what we can do is we can convert each of these values into moles and then do a mole ratio between the H2O and the copper sulfate. Since we know, of course, we just have a 1 over here, right? There must be an X to 1 copper or H2O to copper sulfate ratio, right? XH2O to 1 copper sulfate. So let's go ahead and convert our water into moles. We have 1.04 grams of H2O, and we're going to assume water to be about 18 grams per mole, right? 18 grams of H2O, 1 mole of H2O. Of course, our grams cancel. So when we do this, 1.04 divided by 18, we get about 0.0578 moles of H2O. So let's do the same thing with our copper sulfate. 3.08 grams of copper sulfate. And the molar mass of this, if you look it up, is about 159.609 grams copper sulfate in 1 mole of the copper sulfate. Okay. And what this gives us is 3.08 divided by 159.609. We get about 0.0193 moles of the copper sulfate. So now what we want to do is we want to take our moles of H2O and divide that by our moles of copper sulfate, and that'll give us the essentially the mole ratio between XH2O and 1 copper sulfate, right? So let's go ahead and compute this and see what we get. So if we take our moles of water, 0.0578 moles of H2O, we put it over 0.0193 mole CuSO4, we get 0.0578 divided by 0.0193, about 2.99, right? 2.99, which is approximately 3. So the answer here is letter C, and that means that if we were to write out our formula, we would write it out as copper sulfate trihydrate. Okay, that would be the name of this. Actually, the full name would be copper 2 sulfate trihydrate. Okay, because the copper is in the +2 oxidation state in this compound, right? It has a +2 charge on it. Okay, so let's go on to the next question here. Sketch the optimized Lewis structure of SO2. Keyword here being optimized based on what you've learned about formal charges and such. What is the SO bond order? So if we sketch a Lewis structure of SO2, the first thing that we want to do is count the total number of valence electrons, right? So sulfur is in the same group as oxygen, and each of these has 6 valence electrons. So we're dealing with an 18 valence electron system, right? So let's go ahead and sketch our initial skeletal structure of SO2. So we sketch our initial skeletal structure. We have S, O, and O. That takes care of 4 electrons, so we take away 4 electrons, and we're left with 14 valence electrons, okay? And now what we want to do is populate those valence electrons around the edges, the terminal atoms, because in this case, these are the more electronegative ones, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so we've taken care of another 12 to fill the octets there, but now we have 2 left, and we have no choice but to put them on the central atom, okay? So now we've accounted for all of our electrons, right? So we're good there. But if you notice, sulfur has an underfilled octet, not to mention the overall formal charges here would be a kind of a nightmare. So what we're going to do is we're going to go ahead and make a double bond, right? Move this pair of electrons over here. So we get something that looks like this, double bond. Right? And we could draw a resonance structure of this that's equivalent in energy, right? Just by moving the double bond to the other side. Now, in this case, it's important to notice that for formal charge, we have a plus formal charge on the sulfur, a minus formal charge on this oxygen, and a 0 formal charge over there. If this were, let's say, ozone, where the central atom is another oxygen, then we would have to leave it this way, right? Because we can't expand the octet for oxygen, right? Due to the d orbital levels not being accessible for possible hybridization, or possible mixing in to expand the octet. So in this case, though, we are dealing with period 3 or below, so we can access those d orbitals even though they're vacant, and we can therefore make the argument that sulfur could have an expanded octet. So what we can do is we can move this pair of electrons over here and make another double bond. And if we do that, I'm going to start drawing this out a little bit more in a geometrically reasonable way, right? We get something like this. And notice now all of our formal charges are 0. Okay, so this is the optimized structure. So in this optimized structure, our average SO bond length is double, right, in this case? So if we're basing it purely off of this optimized Lewis structure, then we would say that the bond order, or, you know, is in a sense the average bond type of S and O is a double bond. Okay, so the answer here would also be C, 2. Okay, so we'd say that just based on sort of our rudimentary approach here with Lewis structures, that the bond order is 2. Now, there are much more sophisticated ways of calculating the bond order, one of which is through the molecular orbital theory. And in this case, with molecular orbital theory, what we do is we take linear combinations of atomic orbitals on the different atomic centers that are in the molecule. And that's, a little bit beyond the scope of what we do in this class, but it's something to certainly think about, particularly as you go forward in studying chemistry, is the molecular orbital method. And there is a way to explicitly calculate bond order using molecular orbital theory, but here we just sort of get a rough approximation using our intuition about what can expand octets, et cetera, et cetera. Okay? And how many bonds you have in different resonance structures. Now, of course, here we've chosen, again, to focus on just the most stable structure. All right? Okay. So for number 3, I give you that CCl bonds are considered to be polar covalent. If a typical CCl bond has a measured dipole moment of 1.87 dBi, so our measured dipole moment is about 1.87 dBi, and is approximately 21.9% ionic character. What is the typical CCl bond length, right? So the first thing we have to realize here is that we're given a percent ionic character, so we actually have a way to calculate the sort of theoretical dipole if we were to assume complete electron transfer from, in this case, the carbon to the Cl, right? And so we use this expression where we have mu measured, mu is the dipole moment, by the way, divided by what I'll call mu ideal times 100% gives us the percent ionic character, which in this case is 21.9%, right? So if we go ahead and divide each side by 100, right, we're going to divide each side by 100, and then go ahead and solve for mu ideal, what we're going to get is mu ideal is equal to mu measured divided by 0.219 in this case, okay? And that gives you, when you do these numbers out, about 8.54 dBi, right? Because the mu measured, remember, mu measured is the 1.87 dBi. Now, what we're going to want to do is we're going to want to be able to relate this to the general formula for the dipole moment, which is your mu ideal is equal to Q times R, and Q in this case is the charge of an electron, okay, and R is our bond length that we're solving for in this case, okay, which is really just the distance of the charge's displacement, all right, but in this case we're going to approximate that to be the bond length. So first thing we want to do is get this into proper SI units. And so the way we do that is we take that value, 8.54 dBi, and I gave you that the conversion is in 1 dBi, there is 3.336 times 10 to the negative 30 Coulomb meters. Coulombs times meters, okay? The dBi cancels. And when we do this out, we get about 2.85 times 10 to the negative 29 Coulomb times meters, okay? Coulomb meters. Now, what we can do is we can then substitute this value into this expression over here. So we know that this Q is the charge of the single electron that we're estimating has been completely transferred to the chlorine from the carbon. And of course the charge on an electron is 1.602 times 10 to the negative 19 coulombs, right? So we now only have one unknown, which is our R, or our bond distance. So what we're going to do is we're going to take our ideal dipole, 2.85 times 10 to the negative 29 coulomb times meters, and divide it by 1.602 times 10 to the negative 19 coulombs. The coulombs cancels and we get meters. And when we do this, we get about 1.78 times 10 to the negative 10 meters. And if we convert this into picometers, which would entail dividing by 10 to the negative 12, right? Dividing by, actually, let's see here. I'm getting myself mixed up a little bit. That's why I should write this out. If we convert to picometers, what we're going to do here, look at the top left here because I'm running out of room. We take our 1.78 times 10 to the negative 10 meters, right? And then we know that in 1 meter there would be about 1 times 10 to the 12 picometers, okay? We can see the meters will cancel, and when we do this we get about 178 picometers, okay? And this is answer choice A. Right? So the answer to this question is A, that we can get we sort of estimate the bond length based on this kind of data. Okay. So number 4, I've got sort of this K-type question here where we've got multiple things that you have to consider at once. And what you need to consider is whether or not any of these have an expanded octet. So let's start with W, which is SF4. So if we look at SF4, and we draw the Lewis structure of SF4, we get something that looks like this. Okay, just from a Lewis structure. And we can already tell right away that sulfur's octet is expanded, right? Because we need to be able to account for all the electrons. So keep in mind, each halogen, which the fluorines are halogens, has 7 valence electrons, so 7 times 4 is 28, plus another 6 is 34 electrons, right? 6 from sulfur. So we've accounted in here for all of our 34 electrons, and S indeed expands its octet. So we know at least W is going to be true here. Now, for the next one, BH3, you should hopefully recognize this as just a simple trigonal planar molecule like this. But this violates the octet rule, right? Boron violates it, but it's not expanded. It's not an expanded octet, right? So certainly X is not going to be the correct answer here. Okay. The next one, CH3 NH2, just looks like this. We've got C with 3 hydrogens attached. It's bound to the nitrogen, which has also got a couple of H's attached here. All right, or bound, I should say. And we notice that in this case, we don't have anything that has an expanded octet. And then finally, we've got PCl3. And this is sort of analogous to something like NCl3. But PCl3 got something like this. Right? Yeah, drew my dots a little awkward, but that's okay. And so certainly phosphorus did not need to expand its octet here. Now keep in mind that phosphorus can expand octet, and it does so in the case of something like PCl5, right? But in this case, there was no need to. And in fact, expanding the octet would actually compromise the formal charge, make the phosphorus have a negative formal charge, and would make the terminal chlorine have a positive formal charge, which is just absurd. So the answer here is just SF4 is the only one that will require an expanded octet, and that is answer choice A in this case. Right. Moving on. All right, so number 5 is more straightforward than it looks. So in number 5, you're asked to consider a couple of simple alkenes or halogenated alkenes, okay? And so we have the cis form of this, right, where the fluorines are on the same side of the double bond. And then we also have the trans version of this, which is like this. Okay. And so the question is, choose the best explanation as to why the cis and trans forms cannot readily interconvert with each other. And so the short answer here is that we have inhibited rotation around this double bond, right? So keep in mind, in a double bond, what you have is a sigma bond and a pi bond. In this case, the sigma bond would be between two sp2 carbon hybrid orbitals, right? So this would be an sp2 from the first carbon, and this is an sp2 orbital from the second carbon over here, okay? Overlapping, right? This is an area of orbital overlap. And the overlap of this orbital in the internuclear region is, in fact, what leads to the bond stability, right? The shared electron density between the two nuclei, it's attracted to both, et cetera, et cetera. There's more to it than that, but that's sort of our sort of surface level look at things in terms of chemical bonding. And this thing, notice that if it were just a sigma bond, by the way, this is a sigma bond, right? Because we have this end-on-end type bonding structure, sigma bond. And what we notice is that we can rotate around this without actually breaking the bond or disrupting the nodal structure of the bond. Versus the pi bond that's here, right? The pi bond involves p orbitals that are unhybridized, that are kind of side by side with each other, okay? Now, if we rotate around this, we end up with a problem, right? Because let's say that we rotate around this. One of the things that we end up getting is a configuration of orbitals that looks like this. Spatial configuration is what I mean here. And what we've done actually is we've introduced a node, okay? This is actually a node that would be produced, and it would cancel the electron density, in effect, between the internuclear, or in the internuclear region, right? So this is an unfavorable situation. And so this is precisely why we can't rotate, or there's inhibitions to free rotation around double bonds and triple bonds, is because these pi bonds, right? This is a pi bond, and these are both unhybridized 2p orbitals, right? Each on carbons. The thing that you got to watch out for here is the fact that you would disrupt that in phase combination of the orbitals, right? Because these right now are in phase. You notice the light shading matches the light shading over here. The dark shading matches the dark shading over here, right? And they overlap. Think of that as the sign of the amplitude in a wave function, right? So if you have a wave function, and this is your amplitude, you can have positive amplitude, negative amplitude, et cetera, et cetera. positive amplitude, negative amplitude, and then your node is here where the amplitude is 0, right? So same kind of concept, except what we're doing is we're modeling electrons as waves, right? That's essentially what an orbital is. It's a wave function that describes the behavior of the electron in that particular state, right? But I digress. The main point here is that you can't rotate because these pi bonds would actually essentially be severed, and that's an energetically unfavorable situation to be in, right? So the answer to this question is B, because rotation is inhibited around a double bond. All right, moving on to number 6, which is relatively quick. Consider the chloroacetate anion, CH2Cl COO-. The Cl is bound to the first carbon, the second carbon is bound to the first carbon. The second carbon is also bound to both oxygens. What is the CO bond order for this polyatomic ion? So if we were to draw this out, what we would get is something that looks kind of like this. Okay. Optimize our structure. Okay, and this is the anion, the negative formal charge on the oxygen over here. You'd be thorough and put my lone pair electrons in for chlorine. And here's the thing, is we're focusing in on this COO region, all right? And it turns out we can draw a resonance structure here, right? That is equivalent in energy to the first structure because it's essentially the same thing, right? Just sort of mirrored with respect to which oxygen receives the double bond. Okay. Right? And so what we want to do for the bond order is we want to look at the number of equivalent bonds. So we've got 1, 2, 3 bonds from carbon to oxygen. And then we want to look at the number of equivalent regions, which is 2 here. Okay. An alternative way to frame that would be number of CO bonds over number of essentially energetically equal resonance structures that you can draw. And of course, in this case, we have resonance structure 1 and we have resonance structure 2, and they're energetically equivalent, right? They're indistinguishable in a sense. So what we're going to do is say that the bond order is 3 halves, right? About 1.5. So if you look at the spectroscopic data on this, what you'll find is that the bond stretching vibration is somewhere between a single bond oxygen and carbon-oxygen single bond and a carbon-oxygen double bond, which is consistent. I should say that the theoretical underpinnings here in this model is consistent with the experimentally observed results. Okay, so the answer here is B in this case. All right, so the next one, I admit, is a little bit of a tricky question that I put together here. Choose the compound with the strongest N-N bond. So first and foremost, you should realize that compounds A and C do not contain any nitrogen-nitrogen bonds. So immediately you can eliminate A and C. This is just to make sure you're paying attention. So our other candidate compounds then, or species, I should say, not all of them are technically compounds, is N2O. We've got N3-, which is the azide anion, and we have N2H4. So let's explore these species. If we start with N2O, right, what we have is a 16-electron system, and when we draw our Lewis structure, we get something like this, right? So you get 16 valence electrons minus the 4 that have already been taken into account. And so now we have 12 valence electrons left to account for. Let's fill them in. 1, 2. Oh, whoops. I actually drew another. I'm so used to drawing NO2 that I forgot my other N. Okay, so NNO. 12 valence electrons, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've taken care of all of our valence electrons, which is really great. But now, of course, we notice that this N in the center doesn't have a full octet. So one of the things that we can do to do this is we can borrow a pair of electrons here, right? Make a double bond, right? That's one way that we can do this. And then we can also borrow this pair of electrons and make a double bond there, such that we get something that looks like this. Okay. All right, now you might be thinking, all right, we're done, but let's look at the formal charges. So the middle one, the formal charge is +1. This formal charge is 0. The terminal nitrogen over here is negative. Now, while this is probably at least a relatively low energy structure, one of the issues is that the negative formal charge is on nitrogen, which is still less electronegative than oxygen. So if we have to have the non-zero formal charges, then we might as well make sure that the more electronegative elements receive that the negative formal charge, and then vice versa with respect to the more electropositive elements. So let's see what else we can do. Well, one of the things that we could do is we could make an N triple bond N, right, and leave the O like this, and that way we have plus on the central nitrogen and negative on this oxygen. And so I would say that this is probably the most stable structure that you can draw for NNO. And one of the things to take a look at here, of course, is the fact that the NN bond here is triple bond, right? So that's going to be significant. All right, let's move on to azide, the N3 minus ion. So this is also a 16 electron system, right? Because you have to add the extra electron into the mix. So try to get a little bit of separation here between the species. So for this we have a 16 valence electron system as well. We get N bound to N bound to N. We've now taken care of 4 valence electrons. We're going to get the same deal where we now have to put 12 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Of course, our poor central carbon doesn't have its octet filled, but we can fix that real quick. Move a pair of electrons here, and we can also move a pair of electrons here. And what we see, of course, is that we get N double bond N, right? With our electrons like this, okay? In this case, we have plus, minus, minus, right? So, you know, this here I would say is already a pretty reasonably optimized structure, especially since we know that we're, of course, going to have a non-zero formal charge, but, you know, since all of the elements are the same here, the goal is just overall minimization, not even about where the negatives or positives are placed, okay? And so, of course, the way that we know this is a valid Lewis structure is we add up all the formal charges, and they should give us the formal charge of the overall species, which is minus. Okay? So we've got this. Notice this behaves more like an NN double bond. All right? And then last but not least, we have N2H4. Now the way that we're going to... I forgot to subtract my 12 valence electrons, sorry. So to make sure that we cancel, we accounted for all of them. So N2H4, right, the ends are bound together like this. Right? Again, I'm just doing sort of a rudimentary drawing of this. And then we've got our lone pair electrons here on the nitrogens. Okay? What we notice here, of course, is that we have an NN single bond in this case, right? And there's no really energetically stable way to make a multiple bond, okay, here. So what we find then is the N2O would have the strongest NN bond based on these structures that we've come up with using some very basic tools here, right? So sometimes the more sophisticated tools say otherwise, or get into situations where you might be splitting hairs a little bit, but again, the goal here is to develop a basic chemical intuition, and part of that is being able to compare different species in terms of things like bond length and bond strength and stuff. Okay, so that was number 7. Oh, did I forget to say the letter, right? The letter here, the correct answer is B. All right, the letter, the correct answer is B, which is the N2O situation. Okay, so N2O is correct. All right, upward and onward here. The image below is a skeletal structure of 2,2' bipyridine. All right, so let's go ahead and sketch this real quick, the way they've got it. All right, we got this over here, right? And this and this and this and this and this and this for our double bonds, right? So lone pairs have been omitted, so we want to add our lone pairs in, right? We need to add lone pairs here, and then of course the hydrogens are omitted on these types of structures, skeletal structures, so you have to draw them in if you really want to see them, such that the octet on carbon is filled, right? Okay, so let's take a look. What is the molecular geometry about the nitrogen atoms? Well, each of these nitrogen atoms is identical, and if we look at the, first of all, the electron group domain, 1, 2, 3 electron domains around each of these, so we know that the electron group geometry or electron domain geometry is trigonal planar. Okay. Now for the molecular geometry, we know that because there's just one lone pair, this molecule is going to be bent, and in fact it's going to be bent less than 120 degrees now. Okay. Notice that this isn't quite the same bent variety as when it comes from like water or or something like that from the electron group geometry equals tetrahedral cases. Okay, in that case it would be bent less than 109.5, but in this case we have bent less than 120, and that is the correct answer, and it is answer E. Okay. All right, so let's go on to number 9 here. I ask you to rank the following molecules in order of increasing net dipole moment. So we've got CF4, we've got NH3, we've got CH2O, and we have HI. So right away, if we look at CF4, CF4 is a tetrahedral molecule, both electron group and molecular geometry. All right. Why did I put an H? It should be an F. Goodness, I'm tired. Now, what you notice actually is that if you thought about how tetrahedral structures are, right? Everything will cancel if the bond dipoles belong, of course, to the same connection between elements, right? So in this case, everything is carbon bound to fluorine, and while each individual bond may be polar, right? Partial positive, partial negative, each bond may be polar. The entire molecule is not polar because all the bond dipoles cancel out. Okay, in this case, and it might do you some good to sort of play with the molecular modeling kit a little bit to convince yourself that these dipoles do indeed cancel. Okay, so now we're left evaluating the rest of these. There's a fairly large separation between H and I on the periodic table. H is far up, kind of in the right and to the left. It's the first element on the periodic table, in fact, and then I, is way down at toward the bottom at the far right of the periodic table. Okay, so that's something to keep in mind, in part because I is not particularly electronegative. All right, so that is something to keep in mind. The difference between N and H is a little more stark, and of course for NH3 we also have this this lone pair toward the top there, right? So we know that the net dipoles kind of appear. All right, and then of course CH2O, which is formaldehyde here. We certainly have a decent permanent dipole with the carbon and oxygen. I would make the argument that this one is probably the strongest one of the series here, given where carbon is relative to oxygen on the periodic table, and the fact that oxygen is quite electronegative, right? So our ranking here therefore becomes CF4, right? It has no dipole moment, so obviously it's less than HI, which is in turn less than NH3, which is in turn less than CH2O. Okay? This is what we have got here. Now, number 10, draw the Lewis structure of SF6. According to the valence bond theory, which orbitals overlap between the S and F orbitals to form sigma bonds? So if we were going to draw this structure of SF6, right, we just end up with a bunch of terminal fluorines, correct? And no lone pairs. So we have F, 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 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so this is our entire SF6 molecule here, all right? And so what we want to think about is which orbitals overlap between S and F to form these sigma bonds. So you notice that all these are single bonds, so therefore they're just sigma bonds. Okay, and so what we can do is we can consider the fact that we needed 6 directional areas here, right, of bonding from the sulfur. And so one of the things that this book estimates is that the terminal atoms are not significantly hybridized. So we're going to assume that a 2p from the F interacts with something on the S. Well, what is that something on the S? The thing that it interacts with on the S is the sp3d2 hybrid orbital, right, that comes out of needing these 6 directional regions of electron density, really. Okay, so what we get is the sulfur sp3d2 orbital with the unhybridized, or unhybridized fluoride or fluorine 2p. Okay, and so if we were to then look at this answer choices, we see that the answer choice is D. And again, all these hybrid orbitals kind of all look similar, so you get a situation like this where this is your sulfur, and then you've got it overlapping constructively with, let's say here, this is on fluorine, this is the 2p on fluorine, and then this is the sp3d2 hybrid orbital on sulfur. Okay, so these are the orbitals that are involved and that would overlap here, right? This is our sigma bond to form the bond. Okay, all right, almost there, almost there. Below is the structure of allene. It's kind of a cool structure. Suppose a Cartesian coordinate system is superimposed on the molecule such that the z-axis is going into the plane of the screen or the paper, the y-axis runs vertically, and the x-axis runs horizontally. Which p orbitals on the central atom is or are involved in the pi bonding? Right, that's kind of a mouthful, so let's sketch this out, right? All right, you get something like this. And this, of course, indicates that it's coming out at you, and that it's going behind, sort of away from you, right? Whereas these hydrogens over here are in the plane of the screen, or whatever you're viewing this from. So we're focusing in on this central carbon here, right? That's what I really wanted you to do, is focus in on that central carbon. And what we want to do is we want to superimpose a Cartesian coordinate system here. So this will be our y, and this will be our x, right? And z is actually going into the screen, okay, if you can imagine that. So one of the things that we have to realize here is on the left side of this molecule, all of the sigma bonding takes place in the xz plane, whereas all of the sigma bonding over here takes place in the xy frame. So let's start with the right side. It's actually a little bit easier. If it starts with the xy plane, all right, then what that means is that the unhybridized orbital, in order to create the proper overlap, must be going into the screen. So carbons 2pz, which I'm going to try to draw in perspective here, would interact with the other carbons 2pz unhybridized, right? These are both 2pz's from carbon. And that would create our side-by-side pi interaction, right? There's a pi bond. And that's really between this carbon and this carbon over here, right? So give me 1 second. I've got to get my laptop charger before the laptop dies. That would be a very unfortunate occurrence to happen in the middle of my recording of this. All right. So plug this in. Excellent. All right. So that takes care of the right-hand side with respect to this pi bond, right? But then we, of course, also have a pi bond over here. But notice that all the sigma bonding here this is all in the xz plane, okay? And that leaves y open for pi bonding. So over on the left-hand side, we're going to get the py's to overlap. The 2py from this carbon, which is the central carbon, and the 2py from the carbon next to it to the left here, right? So this is the 2py from the carbon over here. I could label this, let's say this is carbon little a, carbon little b, and carbon little c. And so this comes from, this one over here comes from carbon b, and this one over here comes from carbon c, right? And these are 2pz orbitals. And then over here we've got the 2py. So this one over here comes from carbon A. All right, that's where this orbital comes from. And then this one over here, of course, comes from our carbon B. So carbon B is our true central atom, if we're talking about this, rigorously. So the answer here is D, that the 2py and the 2pz are the orbitals on this central atom that are involved in the pi bonding. Why is that again? Well, it's easier to see on the right-hand side because of how we've drawn the Cartesian coordinate system, but all of the sigma bonding over here is in the yx plane. That means that those p orbitals are getting used up in the hybridization scheme, right? So your unhybridized p is actually on the carbon going to be in the z direction, because it's not part of the plane in which we have the sigma bonding, right? So that's something to keep in mind. So that way this carbon over here, this carbon C, its unhybridized orbital is going straight into the plane of the paper or into the plane of the screen, whatever you happen to be looking at, right? Whereas over here, the unhybridized orbital here is going up and down like this along the y-axis, right? So this is the 2py unhybridized. And that's because, look at where all the sigma bonding is. The sigma bonding is in the xz plane, right? So the unhybridized orbital, the unhybridized p orbital, naturally is going to align itself along the y, because that's not where you need the directional type bonding. Instead, this is going to interact with the py from the central carbon, right, in side-by-side bonding, which is what we call pi bonding. And then, of course, over here on the right-hand side, just to reiterate, that same thing is going to happen, except it's going to be like what I drew down here, right? Going into the plane of the board, because the PZ orbital, unhybridized orbitals, are going to overlap. All right, so hopefully this cleared things up a little bit. I admit I wrote this as kind of a bit of a challenging question, but nonetheless, you should be able to think about kind of what orbitals are involved and in this type of bonding, and what the implications are for having a plane in which we have all of the sigma bonding, for instance, and what the implications are for where the unhybridized orbital will be, okay, or what it will be. All right, and our final portion here of the multiple choice is which of the following species would be expected to have a bond angle larger than the angle predicted from the ideal electron group geometry. So let's take a look quickly at NO2. NO2 has, let's see, 5 plus 12. We have 17 electrons, so we can already tell that this is actually going to be a radical, right, where you have at least one unpaired electron. So we start with our skeletal structure here. This is NO2. Okay. Minus 4 valence electrons taken care of. So we now have 13 left. So you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. So this is the radical, or free radical. All right, so now, obviously, nitrogen's octet is severely underfilled. So let's go ahead and, I don't know, start making some double bonds. So let's put this over there, right? And then let's see what happens when we do this. Right? So what we get is N double bond O, dot, 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 like this. Now, of course, N can't expand its octet. In this case, it's going to underfill it a little bit, right, which isn't great, but it's what we have to deal with here. So now, if we think about the geometry, we've got 1, 2, 3 electron domains. So the electron group geometry, the egg, so to speak, is trigonal planar, right? But then the molecular geometry is a little bit different. Right? The molecular geometry, in this case, because these bonds are being pushed down by the lone electron, right? This molecular geometry is going to be bent. Now, the thing is, and it's kind of giving it away, because there's only one electron here to repel the other areas of electron density, namely the bonds down, all right, we're actually going to get, in this very special case, bent a little bit greater than 120 degrees, right? Because we have less electron-electron repulsion going on there, so the molecule can expand a little bit, and the angles aren't so tight, so to speak. Okay, so certainly W fits the bill. What about NO2 plus? Well, if we write out NO2 plus, what we have is a 16 electron system, right? 16 valence electron system. And so we can start again with our skeletal structure, except what we're going to do this time, there's no more radical, right? So now we can actually take the liberty of making both of these into double bonds and see what happens. Right? And thankfully, our positive formal charge is on the nitrogen, right? And then our terminal atoms, which are more electronegative in this case because it's oxygen, is 0, right? So in this case, what do we have? We just have a linear species, right? A linear species. So there's nothing to talk about in terms of it really deviating, right, from this angle whatsoever. Okay. And then we go on to ozone. Ozone has this kind of structure. You've probably done ozone a lot already. All right. So we won't go through the tedious process of counting up all the electrons. But this is kind of an optimized structure of O3, and of course you can draw multiple resonance structures about this molecule. But of course we still have a full lone pair here, right? And then this double bond is sort of, we have a resonance hybrid that we can draw out, right? In which case we have the double bond is over here, and then the single bond is over here. Lone pair is there, right? But the bottom line here is that we have this full lone pair, so it's going to still repel it enough, even though you have a double bond, right? But it's going to repel it enough that you're going to get a an angle that'll probably be less in this case than 120. Okay, and then finally ICl3. Now, if we look at ICl3, what do we have? ICl3, we have 21 electrons in this case, right? And so if we look at this, Cl, 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 we take our, oh no, we don't have 21 electrons. I totally counted wrong. It's 7 times 4, 28 electrons. Oh, yes, 28 electrons. Ooh, I can count, I promise. 28 valence electrons, right? So we've accounted for 6 here so far. So we've got 22 valence electrons left to account for. Let's populate them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, right? So that's 18 electrons, right? So we now have 4 left to account for. We have no choice but to put those over here, right? Those 4 electrons and minus 4, and we're good. We've accounted for all the electrons, all right? And now, of course, this is just a traditional trigonal bipyramidal electron group geometry because we have 1, 2, 3, 4, 5 groups, 5 domains surrounding the central atom, but then only 3 of them are bonding groups. So what we have is a T-shaped type molecule. But again, there's no expansion of the angles, right? If anything, the angles are compressed in this type of species. Okay. So what I'm going to do is I'm actually going to create a bit of a separate video for the open-ended component. So you can start by looking through this talk through the multiple choice, which I hope you find this helpful. And then once you're done with that, I will be posting the talk through for the open-ended pretty soon. So stay tuned for that as well. Okay, so thank you for your attention.